Okay, so we're going to be doing question 226, inverted binary tree for LeetCode. So this problem, you're given a root, and this root is basically the beginning of a gigantic binary tree. And what we want to do is invert that tree and then return its fruit. So when you look at this example, you're given this gigantic binary tree, and the input is represented as an array, which is kind of just a list of numbers. And for example one, when you look at the tree to the left, this is how it originally looks, right? So you have 4, which is your root. Your root is basically the value all the way on top. And then you have all these little circles here, right? And these are also known as parents and child roots and so on. So with roots, think of it kind of as a linked list, right? But instead of only going right or left, you're going down, left or right. So for 4, for this root, you have a left and a right method, which if you see where I'm highlighting right here, you see how you could do self that left, self that right. So your left will be this 2 and your right will be this 7. These are the children of the root, right? But for the leaf nodes under, these are the parents, right? So the parents are ones where they have nodes under them, and these are the children, right? So for 2, the 2 has a left and a right, and 7 has a left and a right, right? And the nodes under 2 and under 7 are known as children's or the child nodes, right? So what we need to do is now as we kind of know the vocabulary of what is what, we need to invert them. So 4 is going to stay the same, your root is going to stay the same, but for your parent nodes, right, your 2 and 7, you're going to want to invert it. So instead of 7 being to your right, your dot right, we want it to be at your left, your dot left, and vice versa, right? So 2 is dot left, you want that to be to dot right. So how are we going to do that? Well, the first thing we're going to do is something universal. When we're working with binary tree, any sort of question, we're usually going to make a base case. So what is a base case? A base case is basically kind of just a line of code that is going to prevent any errors from happening specifically, well, not necessarily specifically, but for this instance, specifically for binary trees. And how that code is going to look is um, if not root, then return none. So what this is doing is starting at root, when we go down, right, we're constantly checking if we have a left and a right. So if we go down from 4, 4 is dot left, now we have a 2. Does 2 have a dot left and a dot right? It does, right? So we're going to go and check these. Does 1 have a dot left and a dot right? No, right? 1 is the end. This is where it stops. And the same thing applies for 3, right? There's no dot left or no dot right. This is what this line is doing. It's saying if not root, right? If there is no, if root is none, right? If there's no more anything, no value for root anymore, then just return none. That return none comes into play once we start getting around the bottom nodes. So now as we have a base case to kind of prevent us from going off course, we need to now create the code that is going to make the switch. Now how are we going to do that, right? Well, the first thing we're going to do is make a temp variable. And for this instance, we're going to just set it equal to root.left. And the reason why is we're going to be updating the root.left value, right? So we kind of need to make a variable to remember what the original root.left values were. And now these next pieces, lines of code, we're going to have to go through each segment of the tree, right? So we're going to need a segment that goes to the left side, and we're going to need a segment that goes down to the right side, right? So the way we do that is we're going to do root.left equals to go down the left side and root.right to go down the right side, right? And what we're going to do is call um, our function, and this is called recursion. So the word recursion, what it means is when we kind of call the same exact function that we're currently in. And this kind of, what this does is basically, think of it as like a while loop, right? Because you're kind of in here inside the function and you're recalling it, it's going to continue recalling and recalling and recalling itself until whatever it's doing is done, until it returns none, right? Once we finally traverse through the whole tree. So this is what this does. It's important that when doing recursion, You see how we're inside a class, right? And we have self here as one of our arguments. So when we're calling this function, we need to make sure we do self, right? What this does is just, it basically gives us the right to um, run this function within itself. And we are going to go and set this to root.right, right? And we're going to set this to temp. So what is happening is, let's take this aside, right? So let's say this didn't exist. Oh, I didn't want to do that. Let's say that this didn't exist and we just had this. The self.invert tree root right, what this is doing is traversing, right? So we are continuously putting root right inside this function to traverse through the entirety of the right side, right? And the same thing kind of applies here. Um, we are calling invert tree this function right here, and as the argument root, we're putting temp, right? Temp is equal to root.left, so this is going and checking the left side, right? Um, so because of that, um, we now are traversing. Um, we are traversing through the list, but we need to update, right? So it's cool. Yeah, we're going down, we're checking each value, but we need to do the switch now. And the switch happens here inside the arguments. Um, well, not necessarily the arguments, actually, what we're setting it equal to, right? So root.left and root.right. Root.left is basically saying, okay, the left side, right? The dot left points over here where my mouse is at. So when we're setting that equal to root.right, that is making the left value equal the right value. And we're doing vice versa, right? This is exactly why we created the temp variable, is because we're changing what root.left is equal to. We're setting it equal to right. So if left is being updated, then we needed to make this temp variable to kind of store what the left variable initially was equal to, right? So in this instance, root.left is equal, this temp is equal to all this root.left stuff. So now this is saved in this variable called temp. Root.left is then changed. So instead of being equal to this stuff, it's equal to the right stuff. And the root.right, right, this is now equal to the temp stuff. So we're kind of passing like a hot potato situation. And once this is done, remember, all we need to do is return the root. So we're returning the root, which is going to be the same. It's going to be 4. But think of it as a linked list, right? Like when you return the head of a linked list, um, you can traverse through, right? Because now you have the new updated values. This is exactly how it works for a binary tree. You're given the root, your head, right? But you could still traverse through the binary tree because the values are now all updated. So if we were to look at this example right here, right? Dot left, right? Dot left. This line right here. Well, actually, what's more, this line. Invert tree, and your argument is temp. Temp is root dot left. What this does is goes through this whole segment of your tree, right? And invert tree root dot right. So you're calling the function, and your argument is root dot right. This is traversing all through here, right? So if you ever wanted the segment of code to um, to run through the left and the right, or basically just to run through the entirety of a binary tree, it's really important that you remember recursion, which is when you call the function like this, and inside the argument you put in your root and then the method dot right, and then in most instances you don't necessarily need to have a temp variable, so this would just be root dot left. So if we were to run this, you would see that it is accepted. Beautiful. Let's make sure that all the test cases work. And perfect. And you see we have one of the best time complexities as well.